Okay, so here we have an example of similar harmonics where the spring constant is given to us as 75 newtons per meter, and you're given a velocity versus time graph, and you're asked to find a bunch of different parts here. All right, so here we have Vx in centimeters per second, and this uh, graph here traces how an object oscillating back and forth along the x direction indicated by the subscript Vx there. All right, so let's go ahead and show you how to do all this stuff. All right, so I'll do A, B, C, and D on this particular page. So the first thing, hopefully you notice, is that the unit here for velocity in the graph given is in centimeters per second. So you should definitely convert that to meters per second so that all the units for length matches up. So I notice here in the statement, it gives us the spring constant in terms of newtons per meter, but the graph itself is in centimeters per second. So pay attention to units on a graph before you proceed with any sort of calculation. So I went ahead and convert 20 centimeters per second to meters per second here on the right side of the screen. So you should get zero point 0.2 meters per second. To do part A is pretty straightforward. The angular frequency is given by angular displacement divided by time. So which value used for angular displacement doesn't really matter. I'm just going to go ahead and use one revolution. One revolution is easy to do. So on the graph here, you notice I trace here from peak to peak. Anytime you pick the same location and you go all the way to the next location, in this case, peak to peak or crest to crest, is one full cycle. And then the time for one full cycle is given by the function period. And then so period in this case is 1.5 seconds. And then that 1.5 comes from the graph itself. It lies in between 1.4 and 1.6. So if you watch my cursor, if I go all the way up there, that's 1.5 seconds. So in this case, for angular displacement, I will plug in 2 pi rad. Again, I've chosen to use one full cycle. You don't have to. You can do a quarter, a half, 3/4. I just like to use the full cycle. And then in this case, if you use 2 pi rad, you must use the time for one complete cycle, which is known as a period, which is capital T, which I just show you how to do up here. So that capital T, which is be 1.5 seconds. And then we just reduce that. We get angular frequency as 4.2 rads per second. All right. So for part B is super easy. The function for frequency is simply 1 over capital T. In this case, capital T stands for period. We already know the period from part A, so really it's just a plug and chuck now. It'll just be one cycle. In case you're wondering what that one is, it's just one event that happened. In this case, one revolution, one cycle, and the amount of time that it takes for that to occur is 1.5 seconds. So if we reduce that, we should get a frequency of 0.67 hertz. Okay, let's move on to part C. Part C has to define the period, which we already did in part A. So therefore, the period is just 1.5 seconds. All right, so no calculations there needed. For part D, it has to define the amplitude. To find the amplitude, hopefully you're familiar with all these harmonics function. V max is given as the amplitude times the angular frequency. Here, we already know V max from the graph. So I chose to go this route because the graph gave us a maximum value of V max, which is 0.2 meters per second. And then I already know my angular frequency. So to find angular amplitude, I just have to plug and check. So V max from the graph is 0.2 meters per second. And then angular frequency we found in part A, which is 4.2 rads per second. All right, so units cancel out, and it leaves us with just an answer of 0.0476 meters as our amplitude. All right, so let's move on to the rest of the problem. All right, for part E, it asks you for the magnitude, the maximum acceleration. Here it says magnitude because it just looking for the max, so it can be left or right depending on which side the spring is on. But let's just calculate the value of it. All right, so to find A max, hopefully you are familiar with centripetal acceleration. In prior units, centripetal acceleration is defined as velocity square over r. And then, but we know that V is R omega from rotational motion days. So I can go ahead and substitute V is equal to R omega. I'll use parentheses there. So that'll tell me to distribute the square to the R on the inside. It'll also tell me to distribute the square on the omega. Therefore, the R on the top will have R square. It'll be omega square. But since there's an R on in the denominator, it'll cancel out one of the R's on top. So that would just leave me with R omega square. Okay. Now I can use this function for similar harmonics as well, because the motion of an object going in a circle is similar to an object oscillating back and forth on the right or on on a screen. All right, so here I just went ahead and replaced R with capital A, which is the amplitude. The reason I did that is because it's trying to find maximum acceleration, and the maximum acceleration occurs when the block is completely compressed to the left or fully extended to the right, and that distance in simple harmonics is known as the amplitude, okay, which is represented capital A. So if that's the case, we'll use extreme max value. In this case, we found the amplitude already for the mass oscillating back and forth in the previous part, which is 0.0476 meters. And then omega, we found in part A of this particular problem, which is 4.2. And then if you do your calculator work, you should get a value of 0.84 meters per second squared. So not too bad. All right, let's go ahead and do part F. So part F, I'll show you how to do it 3 different ways. Hopefully pick one that makes sense to you most. All right. So the first strategy I have here is just setting up net force equal to the force of the spring. The S here stands for spring. As an object oscillate back and forth along a smooth surface, spring force is the only force present. So if we set that equal to ma, which is equal to negative kx, by definition, net force equal to mass times acceleration. Force of the spring is given by Hooke's law, which is negative kx. However, because we're asked to find the mass, I don't really care for this negative sign because mass is a scalar quantity. We're not adding, we're not subtracting anything. This is simply multiply. So we'll just go ahead and get rid of that negative sign. Okay. Here, I went ahead and isolate for m by dividing both sides by a. But I want to direct your attention here. I replaced x with a being amplitude, and I replace A with A max. So as long as you pick points that correlates to each other, the value should work out just fine. Since I'm using A max occur when the X value is capital A. So be consistent about points, okay? So here I have everything already. K is given in the problem as 75 newtons per meter. I already found amplitude from the previous part. We know A max from the previous parts as well. So if you plug and chuck, you should get a value of 4.25. The second strategy is to use conservation of energy. I know that kinetic energy max is when PE is at its max. So instead of X, I replace X here on the potential energy side due to a spring with A. Again, I'm just setting two maximum points equal to each other. And if that happens to be the case, all of this potential energy is going to go into the kinetic energy of the spring. And this happens at the equilibrium point. And then if you notice here, 1/2 is going to cancel out. So that leaves us with just mv square equals to ka square. And then to solve for m, we divide both sides by v max square. And we know everything already. We know k, we know a, and we know v max. And v max can be pulled from the graph. Again, if you look at this graph, the velocity reaches a speed of 20 centimeters per second, which is 0.2 meters per second. And so we have those values already from the graph. Okay, so plug and chuck, k75, amplitude 0.0476, and then the velocity is pulled from the graph, which is converted to 0.2 meters per second. And then if you do your calculator work, you get the same value. I like this strategy more because it doesn't really, I think it's easier to think about in terms of energy. It has to go all the PE, has to go to all KE. Okay. And the second strategy, excuse me, the third strategy here requires you to know simple harmonics functions a little bit. So here I have the same starting point as this first strategy. Net force equal to the force of the spring. I'll break that up into ma equals kx. You notice here I left out the negative sign in Hooke's law because again we're solving for mass, so that negative sign doesn't do anything. But here I replace a with this particular function here in kind of like a maroon color here, whatever color you want to call it. But if you don't know this particular function, avoid this strategy. A is given as the amplitude omega squared sine omega t. Okay, and then x on this side is given as a sine omega t. Now the reason x and a are sine is because according to this particular graph here in the velocity graph, your velocity graph starts at max, which implies that x is equal to 0. So again, maximum velocity occurs at the equilibrium point. So it suggests that your x at 0 second starts at 0. And if that's the case, according to this graph, that'll be a sine graph. So if x is sine, velocity will be cosine, which is what you're given. And then if velocity is cosine, your A graph will be a sine graph. Okay. So to help you visualize, in case your sine and cosine graph visual is not in your head, I have this image up here in blue. Okay, it's our cosine graph. what I'm tracing out there. And that mirrors what we're given in the velocity graph here on the left side, because it starts at times equal to 0, it starts at a maximum value. So if that's your cosine graph, your x to t graph will be a sine graph according to calculus. Okay. Other than that, we can just go ahead and simplify the stuff here. Again, if you don't know the stuff in pink here, I would avoid the strategy. All right, I'm just going to cancel out A out. And then I notice here we also have omega sine omega t on both sides. So I'm just going to cancel those terms out. So this reduces down to simply m omega squared equals to k. To find m, we divide both sides by omega square. And then here we have k, we have omega square from the other parts. And k is given. Omega is calculated in part A as 4.2. So if you do that correctly, you'll get 4.25 kilogram as well. So pick a strategy that you like, that makes sense to you most, and then hopefully stick with it. And then part G asks us to find the equation of motion for this oscillator, aka x to t. But if you understood this strategy here on the right, where I'm circling with my cursor, x of t is just given by a sine omega t, and so that would just be our answer. Okay, so if you are not familiar with sine and cosine, I encourage you to graph a few functions and then hopefully see how things are related. All right. Other than that, stay nerdy. Don't be whack.